Welcome to our course in Sensing Technology in Building Services. This course is accredited by CIBSE for CPD. Topics covered in this presentation will be a brief history of sensing technology, the role of sensors in a modern BMS, importance of high-quality sensors, energy-saving technology, common sensor types used in building HVAC, digital technologies, and a summary. The learning objectives of this course are to develop an understanding of the role of sensors, the importance of accurate sensor data, how sensors communicate with BEMS, different sensing technologies used within building services, how sensors are used to help save energy, how sensors offer an important part of data acquisition strategies. We will start with a brief history of sensing technology. Here is the timeline of sensing technology, starting from 1883 when Warren Johnson patents the bimetal thermostat, all the way through to 1995 where the BACnet standard is published, ushering in the age of smart sensing. The first commercial thermostats became available at the end of the 19th century. Commercially viable resistance, temperature detectors and other semiconductor devices began to appear in the 1930s. Initially designed for high-end process applications, the ever-decreasing price of electronic components ensured that such devices were eventually viable for building services control applications. By the 1970s, pneumatic control was in decline, as discrete electronic systems became the standard for provisioning building control solutions. Further advances in technology permitted a vast range of sensor types to become available. By the end of the 1980s, discrete electronic devices were being superseded by microprocessor-based direct digital control solutions. However, the sensing devices remained relatively unchanged, with DDC controllers requiring sensors for input in order to perform control algorithms. Although not the first open protocol, the publication of the BACnet standard in 1995 provides us with a marker for the advent of the smart sensor. Unlike their predecessors, smart sensors are able to communicate multiple values on a single network bus, reducing physical input or output requirements on DDC controllers, and increasing the flexibility of the sensing devices themselves. The role of sensors in a modern BMS. We will look at the BMS input and outputs, how sensors communicate values to the BMS, and how BMS processes the data. BMS inputs and outputs. BMS controllers are computers. They accept inputs and provide outputs based on a set of instructions, which we refer to as the program. Sensors are connected to the input terminals to provide either a digital, on and off status indication, or an analog value. Sensor information can include temperature, relative humidity, air quality, and airflow status, but there are many others. This presentation concentrates on the use of sensors connected to input terminals of BMS controllers. There are many different types of controller, but the same principle applies, regardless of the system in use. Controllers are equipped with inputs and outputs defined as either digital, having only two states, on and off, or analog, meaning any value within a given range can be achieved. When we talk about sensors, we are generally referring to analog sensing devices, whereas digital devices are most currently referred to as switches or stats. For example, a temperature sensor refers to a device where any value can be read within the sensing range, whereas a thermostat switches either on or off as temperature passes through the set point threshold. How sensors communicate values to the BMS. Sensors are transducers. They convert physical variables to an electrical signal. Traditionally, this has been a change in resistance, voltage 0 to 10 volts or current 4 to 20 milliamp. Smart sensors, covered later, provide the same information, but it is encoded and sent via a digital bus. The BMS industry uses 3 common signal types for sensors. Active sensors have onboard electronics which provide a linear output voltage or current signal. Although other scales exist, the most common active signals are 0 to 10 volts DC or 4 to 20 milliamp. Passive sensors do not have any onboard electronics and rely on changing physical conditions to vary the signal. Modern smart sensors do not provide a variable analog output signal, but instead they communicate their values via a digital bus. These signal types are discussed in more detail later in the presentation. How BMS processes the data. The electrical signal is compared to a scale to provide a value for the measured variable. Linear signals, for example 0 to 10 volts DC, use a formula to calculate the entire range. An example of this would be 0 would be 0 degrees and 10 volts could be 100 degrees. That's how the controller would read the scale. Non-linear variables such as resistance from temperature sensors use lookup tables to linearize the information and provide a value for any point on the curve. For linear signals such as 0 to 10 volts DC, we simply need to take the voltage and multiply it by a factor, a coefficient, to ascertain the corresponding value. Non-linear signals, such as those derived from a thyristor, need to be linearized. Linearization is the process of selecting multiple points on the temperature resistance curve and providing a coefficient for each segment, corresponding to the steepness of that part of the curve. These are often called lookup tables. Different BMS controllers require you to set up this in different ways, but the result is always to provide an accurate as possible value based on the resistance measurement. The more points you define in a lookup table, the more accurate your readings will be across the entire sensing range. The importance of high-quality sensors. The importance of accurate information and inaccurate sensing example. Importance of accurate information. Inaccurate sensor measurements result in poor control. Inaccurate input values can result in greater output errors magnitudes. Poor control results in increased energy consumption. Trend information is incorrect, and data analysis algorithms are only useful when performed on an accurate data set. The purpose of a controller is to eliminate any difference between a set point and a measured value. If the value that you are feeding into a control process is not accurate, then the result that you will generate when trying to eliminate the control difference will also be inaccurate. The result output may be many times greater, as is shown in the example on the following slide. Data analytics is a huge industry, and crunching large sets of building information can give valuable insights into building control anomalies. However, results from analysing a data set are only as accurate as the information stored in the database, and getting the sensing technology right at the outset is a crucial first step in generating meaningful output from analytical software. Here is an example. In step 1, the sensor value is compared with the set point to calculate the control difference, or the error. If the sensor reading is inaccurate, then the calculated control difference will be incorrect, possibly causing a control action when none is required. Step 2. The control output is calculated by multiplying the control difference by a fixed controller gain. The controller gain is essentially an amplifier, and an incorrect sensor value will result in an even larger inaccuracy in the controller output Step 3. The sensor will continuously monitor the output of the loop and report a value different from the actual physical conditions. Whilst the system will ultimately come under control, the conditions will be consistently incorrect due to the inaccuracy of the sensor. Energy saving technology. We will cover variable speed drives, weather compensation, and natural ventilation. Variable speed drives. Modern HVAC systems use variable speed drives, VSDs, to control the speed of fan and pump motors. VSDs control the frequency in hertz of the electrical supply to a motor. Reducing the frequency reduces the motor speed. There is a cube law relationship between reduction in speed and reduction in energy consumption. As an example, a 20% reduction in speed will result in a 48% reduction in energy consumption. Dropping a motor frequency from 50 Hz to 40 Hz will almost halve the energy used. Sensing technology plays a vital role in providing the data to reduce motor speed and save energy. In-depth knowledge of the workings of a VSD is beyond the scope of this presentation. However, the important factor is the non-linear relationship between motor speed and energy consumption, which follows a cube law relationship, meaning that any percentage reduction in speed will result in a much larger reduction in energy consumption. In the example above, we are reducing the speed by 20% of its previous value, i.e. the new speed is 80% or 0.8 of what it was. Using the cube law, we can calculate that the corresponding power reduction will be 0.8 by 0.8 by 0.8, which equals 0.512 or 51.2% of its previous value. Slowing fans and pumps down from their full operating speed is a common way to significantly reduce HVAC operating costs. Using sensors to measure variables which will enable demand-based delivery of air and water is a key part of this process. Weather compensation. Comfort conditions within a building are dependent upon ambient conditions. The relationship between outside and inside conditions has significant effect on occupant comfort. Correctly monitoring these conditions facilitates optimization of the HVAC plant to minimize the heating or cooling requirements. Monitoring outside air humidity conditions can significantly reduce cooling energy requirements for systems equipped with recirculation dampers. There are many weather compensation strategies deployed within HVAC schemes. A very common method of conserving energy is to reduce the temperature of the water being delivered to the radiator circuit as the outside air temperature increases. Outside conditions also play a vital role in saving energy on systems equipped with mixing dampers. Sensing dry bulb temperature and relative humidity both internally and externally will allow the engineer to calculate the combined sensible and latent heat content, enthalpy, of the air at each part of the process. Operating a system like this in full fresh air mode when there is cooling requirement and high outside enthalpy is extremely energy wasteful, as the mechanical cooling system will need to remove large quantities of latent heat from the air, with little resultant air temperature reduction. Choosing the correct sensing arrangement is important when installing such a system. Natural ventilation. Natural ventilation is the process of providing ventilation without the use of mechanical fans. It also encompasses technologies such as free cooling, where outside air is used to cool a space. Many nighttime pre-cooling strategies use cooler night air to pre-cool a building. Correct measurement of conditions such as air temperature, humidity, and wind speed and direction are vital to the successful implementation of these strategies. Although natural ventilation can be as simple as opening a window, Automating the process will help maximise the benefits of natural vent schemes, whilst maintaining comfortable internal conditions. Strategies utilising natural ventilation need to have input on air temperatures, wind speed and direction in order to provision this functionality. Nighttime pre-cooling routines need accurate information on many parameters to ensure pre-cooling is provisioned with no detrimental effects, such as condensation forming on the conditioned space. Common sensor types used in building HVAC: temperature, relative humidity, CO2 and air quality, air and water differential pressure, electrical current, and occupancy. Temperature sensors. Here are some common types. A space temperature. Aesthetically sympathetic enclosure, often incorporating other controls such as set point adjusters. Flying lead sensors. Compact all-in-one sensor and cable, mainly used on return air paths for fan cool units, but also seen in underfloor heating applications. Duct temperature, used in air transport ducts to measure central air distribution temperature. Immersion temperature, internally sealed sensing elements designed to be located in immersion pockets for fitting in areas like tanks or pipework. Outside air temperature, weatherproof enclosures, sometimes fitted with radiation shields, for use in direct sunlight. Choosing the correct sensor type and installing it properly is one of the most important parts of provisioning building control. Different sensor types are manufactured for different purposes, and it is important to select the correct device for the application. Temperature sensors come in many different formats and are not universally interchangeable. For example, duct and immersion probes often look the same, but internally immersion probes contain a resin to prevent condensation forming in the sensing tube in chilled water applications. Using a duct probe instead of an immersion probe will likely result in premature sensor failure. One universal rule when selecting sensors is to try and sense the temperature at the point you are trying to control. Flying lead sensors attached to the back of a fan coil unit in a full ceiling is the compromise, to be used in large open plan office spaces. Better results will always be achieved by using a space temperature sensor located at the correct height in small spaces, such as partitioned offices. Different temperature sensor types have different responses. RTDs tend to provide a faster response to temperature changes than thermistors, but are usually more expensive. If the application requires a fast response, it is important to select an appropriate sensor type. Temperature sensors, applications. Comfort of occupants. Most people are comfortable within a temperature range of 20 to 24 degrees Celsius. Asset protection. Equipment such as computers produce large amounts of heat, which require accurate temperature monitoring and control. Frost protection. Water expands as it freezes, which can damage pipework and cause leaks. Condensation protection. Low temperatures can cause condensation to form on surfaces, leading to material damage. The primary reason for sensing temperature is to provide comfortable conditions for building occupants. However, some applications, such as data centres, require accurate temperature monitoring to ensure the excess heat generated by IT equipment is removed from the space in an energy-efficient manner. Temperature sensing is also vital in providing frost protection to water systems susceptible to low temperatures. Water expands as it freezes, which exerts huge pressure on pipework systems and can cause weak points to rupture, causing a leak when the system thaws. Temperature sensors, signals. Controllers can receive data as signals from different types of sensors, such as analog PTC and NTC sensors, passive temperature sensors with thermistor or RTD. These are a lower cost option and have a non-linear response. There are active temperature sensors, which can be 0 to 10 volts DC or 4 to 20 milliamp. These are characterised by a linear output. Smart temperature sensors have lossless digital bus signal and Modbus and BACnet MSTP over RS485. For HVAC, the most common type of passive sensor is a thermistor, a thermal resistor, which provides a varying resistance as its temperature changes. Resistive temperature detectors, or RTDs, are similar to thermistors in that their resistance changes with temperature, but there are some differences. RTDs show a very small shift in resistance over their sensing range. The response is relatively linear and they have a positive temperature coefficient, which means that as the temperature increases, the resistance of the detector increases. Conversely, thermistors generally have a negative temperature coefficient, a large change in resistance and a very non-linear relationship between temperature and resistance. Each type of resistance temperature sensor has its own set of benefits, and it is important to choose the correct sensor for your application. Active signals are generally either 0 to 10 volts DC or 4 to 20 mA. In the case of a temperature sensor, this is generally derived using a platinum RTD inside the sensor unit, which is then fully linearized as an active output. Most other sensors, for example relative humidity or pressure sensors, have active 0 to 10 volt DC or 4 to 20 mA signals, and passive signals are uncommon outside of temperature sensing. Smart sensors provide lossless digital signals to communicate their values back to the BMS. These are covered separately near the end of this presentation. Measuring humidity. There are 3 different types of humidity measurement. Specific volume. Volume of air increases as it expands due to temperature increase. Absolute humidity. Constant regardless of air temperature. The quantity of moisture contained in a given quantity of air, grams into kilograms. Comfort effective if values exceed 11 grams per kilogram. Relative humidity. Affected by air temperature changes. The relative quantity of moisture contained in the air as a percentage of the maximum amount of moisture at that temperature will hold. That's a percentage of RH. Comfort levels are around 40 to 60% RH. There is a huge focus on temperature when trying to achieve comfortable conditions within a building. However, the importance of the correct humidity conditions should not be overlooked, as this also has a significant impact on occupant comfort. Generally, conditions between 40 to 60% RH will be comfortable for most people through the absolute humidity does play a role in thermal comfort too, when it gets to very high levels. Absolute humidity is the mass of water in grams per mass of air in kilograms, and is constant regardless of air temperature. Having more impact on our comfort, relative humidity is dependent upon the specific volume of the air. Like any other substance, air expands and contracts as it changes temperature, and therefore the specific volume of a kilogram of air will change as the temperature changes. Along with this change in volume is the air's capacity to hold evaporated moisture. A kilogram of warmer air has a larger volume than the same kilogram of air at a lower temperature, and can hold more moisture as a result. Therefore, the amount of moisture contained in a kilogram of air relative to the maximum amount of moisture air at that temperature could hold is expressed as a percentage of RH. Because the air's capacity for holding moisture fluctuates with temperature, the relative humidity value is dependent not only upon the amount of moisture in the air, but also the temperature of the air. Relative humidity sensors. Here are some common types. A space RH&T, which has active outputs for space temperature and relative humidity. Duct RH&T, which is used to measure temperature and relative humidity in supply and extract airflows. An outside RH&T sensor. Various different designs to monitor outside air conditions. Humidity sensor elements need to be protected from water ingress to avoid incorrect readings. They also are protected with a radiation shield in sunny positions. Measuring relative humidity is commonplace in ducts and conditioned spaces. Some applications require measurement of outside relative humidity, and thus some means of protecting the sensor from water ingress is important. On large-scale systems, this is often achieved by using an aspirated chamber, full protected from the elements, but another common method is to protect the sensor element itself by using a range shield. Relative humidity sensors. Applications. The comfort of occupants. Generally, people are comfortable within a relative humidity range of 40 to 60% RH and an absolute humidity value below 11 grams per kilogram. Static protection. Low relative humidity increases the risk of static electricity discharge. Measuring and maintaining correct RH levels is an important part of data center control. Dew point sensing and control. Passive technologies such as chilled beams must operate above dew point temperature to avoid condensation. Dew point temperature can be calculated using RH and space temperature. Controlling comfort conditions is a key driver for humidity sensing, but there are other applications requiring accurate measurement of relative humidity. The risk of static electricity discharge increases as relative humidity falls. Electronic equipment is susceptible to damage from static discharge, and maintaining the correct relative humidity conditions in spaces such as data halls reduces the risk of this occurring. Another important use of relative humidity sensors is in the calculation of the current dew point temperature. Dew point temperature is the temperature at which condensation will start to form on surfaces, based on the air temperature and moisture content. Preventive passive cooling devices such as chilled beams and chilled ceilings from falling below dew point is important, as these cooling systems have no means of collecting condensate and directing it into a drain. Measuring CO2 and air quality. CO2 sensing. The concentration of CO2 provides an indication of building occupancy. Using the value to control ventilation rates to comfort levels, approximately 1000 ppm saves energy. Air quality. It measures the level of volatile organic compounds, VOCs, in the air. High levels of VOCs can lead to ill health effects such as headaches, dizziness and nausea. Good quality air is another factor affecting the well-being of building occupants. Ventilation is provided to maintain good air quality, but a distinction should be made between the requirement to sense carbon dioxide and the requirement to sense general air quality. Carbon dioxide measurements are intended to give an indication of the occupancy level of a building, whereas the air quality sensors sense a combination of airborne pollutants, including carbon dioxide. The correct sensor must be used for the required application, and when implementing demand-controlled ventilation, good quality carbon dioxide sensors are required rather than air quality sensors. More details on these applications are given in the following slides. CO2 sensing applications. High CO2 levels cause occupants to feel lethargic. Mechanical ventilation is designed to provide 10 litres per second per person of fresh air into the space to maintain comfort in office environments. Because we exhale CO2 at a steady rate, measuring the concentration in the space gives us an indication of occupancy levels, and we can adjust the ventilation rate accordingly. This reduces fan energy consumption. Demand-controlled ventilation requires a measurement of anything which gives an indication of the number of occupants within a space. Because we exhale CO2 at a constant metabolic rate, we can use the concentration of CO2 in the space to give an indication of the number of people in a space, and therefore how much fresh air needs to be provided. Higher concentrations of CO2 indicate higher occupancy, requiring additional fresh air delivery, and conversely lower CO2 levels indicate that less fresh air is required to meet the needs of the occupants. Subject to a minimum fresh air rate, when CO2 concentrations start to fall, we can slow the fresh air fans down to deliver less air and benefit from the energy savings afforded by a VSD when running a motor at a reduced speed. Comfortable conditions are usually around 1000 to 1500 ppm, but different scenarios require different ventilation rates. Lower CO2 levels aid people's ability to concentrate, and many educational specifications now require a level of 750 part per million. VOC sensing applications. A VOC is any substance which exists as a gas at a normal room temperature. Common VOCs causing discomfort to building occupants are fumes from cleaning products, cooking, decorating, and new furnishings. By sensing the air quality, it is possible to adapt minimum ventilation rates to match the building requirements. Volatile organic compounds are not as menacing as the name suggests, and include any substance which exists as a gas at normal room temperature. Cleaning fluids are one of the most common sources of VOC in commercial applications, and by sensing the VOC level along with the CO2 level, the minimum operating speed of the fresh air plant can be adapted to operate at its lowest permissible level based on actual conditions. Commercial kitchens are another space where VOC monitoring can be beneficial. Kitchen ventilation requirements tend to be high, but only when cooking is taking place. At other times, the ventilation rate can be slowed to match the activity in the space, thus reducing fan energy consumption, which can be achieved by sensing the concentration of VOCs within the space. Pressure switches and sensors. Pressure switches are lower cost devices which activate at a preset threshold value. Analog pressure sensors provide an output signal within their predefined sensing range. There are three main types of analog pressure sensors used in HVAC applications: air differential pressure sensors, liquid single point pressure sensors, and liquid differential pressure sensors. This presentation focuses on analog sensors. However, it is worth mentioning pressure switches as there are a particularly high number of these low-cost devices used to monitor flow status and filter dirty indication throughout HVAC applications. Like their switched counterparts, pressure sensors have either a diaphragm or piezo-resistive element, which reacts to pressure being exerted upon it. We see the three main variants of pressure sensor used for HVAC applications. Air differential pressure sensors. Pressure is applied across the diaphragm. The amount of deflection relates to the differential pressure value in pascals. Applications include fan speed control, filter dirty status monitoring, air pressure alarm generation, and air velocity and volume measurements. Air differential pressure sensors can be used to sense static pressure in an air duct and control fan speed to maintain a constant pressure. This is especially important for variable air volume systems, which require a constant static pressure in the supply duct. Under partial load conditions, the VAVs will shut down, causing an increase in duct pressure, which can be used to slow the fan down. Air DP sensors can also be used to monitor differential pressure across filters, giving a much better indication of how dirty they are. Air DP sensors can also be used as the input for alarm generation, although it is common to use switches rather than sensors for this. Using a sensor allows remote adjustment of the alarm threshold and also multiple alarm thresholds from the same sensor. Although not covered here in great detail, air DP switches can be used to calculate air velocity and volume. Using a suitable probe in the air duct, a differential pressure measurement is taken between the total duct pressure and the duct static pressure. The resultant differential reading is the velocity pressure, which can then be passed to an equation to calculate velocity in meters per second. By multiplying this value by the cross-sectional area of the duct, measured in meters squared, the flow volume can be ascertained in meters cubed per second. Liquid single-point pressure sensors. These are generally designed to sense higher pressures than air DP units. Pressure acts on one side of piezo-resistive element, allowing the liquid pressure to be measured. The output signal relates to the system pressure and is usually measured in bar. 1 bar equals 100,000 pascals. Applications include leak detection, system pressure alarm generation, pressurization and system control. Single-point pressure sensing in a liquid system can be suited to general alarms for under or over pressure events, as well as control pressurization of the system. A common use for pressure sensors is for leak detection, where a sudden or sustained drop in pressure might indicate a leak. Sensing mains incoming pressure allows the building owner to monitor the stats of the utility supply to the building. Liquid differential pressure sensors. Pressure acts on both sides of a piezo-resistive element, allowing the liquid differential pressure to be measured. Applications include pump speed control, volumetric flow measurement, and system DP monitoring. Used in a similar manner to air DP sensors, one of the main uses of a liquid DP is to control the speed of a pump. The rise in the number of two-port control valves allows the system to be controlled using a differential pressure sensor to maintain a volumetric flow through the system matching the load. As the two-port valves close down, the volumetric flow reduces and the pump differential pressure increases. By sensing this increase in pressure differential, the pump can be slowed down to match the operating point of the system. As with air DP sensors, liquid DP sensors can be attached to Venturis or orifice plates to ascertain volumetric flow based on variances in differential pressure. Current sensors. Current sensors measure the current passing through a wire. As the current increases, the output signal will rise in a corresponding manner. Current sensors have a specific range and should be selected depending on the size of the load being monitored. Applications include energy usage monitoring, reactive plant optimization, and automated fault monitoring and condition-based maintenance. Current sensing offers a number of benefits. Current sensors can be used to monitor the status of pump and fan motors, were it not possible to use a differential pressure sensor. This includes retrofit applications where drain down is prohibitively expensive, and for HWS return pumps where the control of Legionella precludes the use of differential pressure monitoring. Rudimentary power calculations can be performed using a current sensor by assuming that the supply voltage is constant. Condition-based monitoring allows alarms to be generating when current demand exceeds a given threshold. For example, variance in fan power that would be seen from a broken damper or other blockage. Occupancy sensors. Occupancy sensors detect the level of passive infrared radiation. Units are generally sold as a package controller, some with a user-adjustable sensitivity set point. Motion will activate the sensor, indicating that a space is occupied. Similarly, a lack of motion will indicate that a space has been vacated. Applications include lighting control, HVAC control optimization, and demand control ventilation. Occupancy sensing offers many possibilities for the reduction of energy use. By using occupancy detectors, HVAC plant can be operated in a standby mode during the defined occupancy period, but when there is no actual occupancy detected. An example of this would be a fan cool unit serving a meeting room with a temperature set point of 22 degrees C. In standby mode, the unit has a temperature controlled dead band of 4 degrees C, meaning a heating set point of 20 degrees C and a cooling set point of 24 degrees C. Once occupancy is detected in the meeting room, the dead band is shifted to 2 degrees C to improve comfort and is then reverted to standby mode once the room is vacated. Occupancy detection can also be used for demand-controlled ventilation schemes, so that only minimum fresh air is supplied to unoccupied spaces, with the ventilation plant ramping up when occupancy is detected. Now let's look at digital technologies. They include smart sensors, wireless sensors, and Internet of Things. Smart sensors. Smart sensors have integrated communication capability, allowing them to transfer their information via a digital bus rather than an analog signal. Multiple sensors can be installed on a single digital cable segment. Digital transfer of data reduces inaccuracies due to installation conditions, such as cable type and length, etc. Multifunction sensors can provide additional data over the same wires. Advances in technology have given rise to increased functionality from smaller devices. Sensors with built-in microprocessors now provide multiple functions in a single unit, complete with communication capabilities. Digital technology allows all values to be passed down a single bus cable, making it possible to daisy-chain sensors, reducing installation time and cost. Values are digital and are therefore not subject to issues such as voltage drop along the connecting cable length. Here is the Smart Sensor Data Network. It consists of twisted pair EIA485 or RS485, which has emerged as the most favoured network type for connecting smart sensors. RS485 networks must be installed using cables with a particular characteristic and will generally need to be terminated using a resistor at either end of the line. An RS485 segment will support up to 32 individual devices, though this can be extended using data repeaters. Generally, speeds of up to 256 kilobits per second are supported by HVAC products using RS485. EIA485, or as it is more commonly known, RS485 twisted pair networking, is a well-established technology. The 2-wire variant of this is used in many different devices to carry data using both open and closed protocols. It is important to use the correct shielded twisted pair cable and to install it properly with screens connected to a potential earth at one end of the cable only. It is generally necessary to then terminate each end of the cable with a 120 ohm resistor to prevent data reflections, which will cause anomalous readings and interference. Maximum bus length is dependent upon the baud rate, but at speeds of up to 90 kilobits per second, a 1200 metre should be achievable. Smart sensor protocols. RS485 supports many different protocols, but Modbus RTU and BACnet MSTP are the most widely used. Both are open protocols and are therefore vendor independent, offering excellent interoperability with other devices. Modbus is a lightweight protocol well suited to smaller devices with minimal resources. Modbus sends simple data packets only, and information needs to be interpreted by the receiving device. BACnet MSTP is an open standard developed by ASHRAE specifically for managing communications for HVAC equipment. BACnet MSTP permits the sending of additional information such as identification labels and alarms directly from the smart sensor to a receiving device. RS485 is the physical network. In order to communicate between devices, it is necessary for all devices to be using the same protocol. Smart sensors will typically use one of two protocols, Modbus or BACnet MSTP. Modbus was invented in the 1970s by the Modicon Corporation as a means of exchanging data between process control systems. The limitations of technology at the time required it to be very lightweight protocol, operating at a low baud rate. It was never developed as an open protocol, but has emerged as such, with the owners putting no restrictions on Modbus. But the lack of a standard and the hex coding system used can make it tricky to work with. Because of its simplicity, it has been integrated into smaller and smaller devices and has a reputation for reliability. BACnet was developed by ASHRAE, the American Society for Heating, Refrigeration and Air Conditioning Engineers, and the first standard was published in 1995. It was specifically designed for building automation applications and has strict rules regarding language constructs, minimum requirements and transmission media. BACnet MSTP, master-slave token passing, uses twisted pair RS485 as its transmission medium and is commonly found in smart sensors, actuators and many field devices. Both are open standards. That is to say that anyone can implement the protocol on their device without the need to purchase a license to do so. BACnet, however, does have an accreditation scheme where a vendor can get their device tested for compliance with the BACnet standard in order for it to bear the BTL mark. It should be noted that it is not a requirement of the BACnet standard for a product to be BTL marked, and there are many non-BTL marked devices which fully comply with the BACnet standard. Wireless sensors. Wireless technologies communicate their values to a receiver, which typically then relays information to the BMS via a wired connection. They offer reduced installation costs due to minimal wiring requirements. Highly suited to retrofit applications, but properly planned wireless networks can also reduce installation costs for new projects. Digital communications allow acknowledgement of receipt of sensor data. Self-healing network topologies allow signals to be routed via multiple paths, making the sensor network resilient. Wireless sensing has been around for many years and has evolved from single point-to-point sensor receiver systems to complex mesh networking topologies. Full mesh networking is difficult to implement using battery-powered devices, and a common topology is the self-healing tree network. A base station relays sensor data to a wired link and can communicate directly with sensors via powered wireless routers. If communications to a router cease to be available, the sensor will find its next nearest router and continue to communicate to the base station via the new route. Internet of Things, or IoT as you may understand it. IoT refers to the prolific rise in devices capable of machine-to-machine communications over TCP or IP networks. An IoT sensor would be equipped with some means of sending its data to another machine via a TCP or IP packet. Typical IoT setups use a publish or subscribe model, where a broker acts as the intermediary between devices, sending data and those requiring the data. MQTT, message queuing telemetry transport, is emerging as the protocol of choice for IoT technology. As smaller devices support more complex applications, it is now possible to communicate values directly from sensors using Internet protocols. The Internet of Things is used to describe the emergence of machine-to-machine communication across the Internet. The MQTT protocol is widely used for the secure exchange of data between devices. Developed by IBM as a lightweight messaging protocol, its publish-subscribe model is well suited for machine-to-machine communications and so is a good fit for IoT. The IoT publish or subscribe model. Using this method of communication, a sensor would be set up to publish its data to a topic in an MQTT broker. Any device requiring that information would subscribe to the topic in the MQTT broker. When new information is published to the broker by the sensor, the broker then pushes that information out to the subscribers. The broker is not a database. It simply handles the information exchange between publishing devices and subscribers. A subscriber could be a database application which stores the sensor information each time it is published. The diagram shows the flow of data from the sensors located in client B to the broker, which then disseminates the information to other devices which have subscribed to this information. A single sensor value can be made available to multiple locations through the broker. As an example, a space sensor may publish its data to space temp topic at the broker. A heating control application running on a server and a database application may be subscribed to this topic, and each will receive the new data as it's published. The database application will store the new value with a timestamp, whilst the heating control application will use the data to switch the heating on or off, possibly by publishing a status to the broker, which is subscribed by a smart actuator. Now let's look at some case studies where it is demonstrated how important sensing is in any BMS. Club Mac Hotel. The Club Mac site covers an area of 100,000 square metres and is made up of 3 different buildings called Jupiter, Marte and Saturno. Cirque Bolaris worked on a complete migration and expansion of the BMS for the entire hotel complex. The Sonte sensors are helping the hotel reduce energy consumption by an impressive 40%. The requirement is to increase comfort for guests in all areas of the hotel. The hotel wanted to be as efficient as possible to save both energy and money. The Sonte products used the relative humidity RH1000 AH space sensor, the duct RH622 sensors for RH, and the RH632 outside sensors. They also use TT341 immersion sensors, TT555 flying lead sensors, PL528 10V static pressure transmitter, and LLEV outdoor light level sensors. Hotels are an area where selecting the correct sensing technology presents a number of challenges. Front of house systems, particularly in guest rooms, need to be both unobtrusive and tamper resistant. The overall scheme needs to have reliable sensing technology in multiple locations to ensure that the control scheme can accommodate differing occupancy patterns, depending on seasonal demands. Back of house systems, such as kitchens, also rely on accurate sensor data to ensure optimal operation of ventilation systems. As an example, reducing ventilation rates when cooking is producing fewer fumes or during quieter periods. Goldstone Shopping Centre. This project was completed in 2016. It consists of 3 22-floor tower blocks built in parallel, with 4 floors being built underground. Once completed, the buildings will cover 240,000 square metres, with 120,000 square metres of office space and 120,000 square metres of retail and parking space. The requirement was a complete BMS and energy-saving climate control solution that meets Western standards. The system needed to be reliable and accurate. Within this, they used Sonte products such as the PA699 multi-range differential pressure transmitters, the TT341 immersion sensors and TTPO521 immersion sensor pockets, along with PL528 static pressure transmitters. Accurate sensor data is key to optimising any facility, and none more so than shopping centres. Maintaining correct pressure regimes between the mall and shopping units is an important consideration when developing energy-efficient strategies. Similarly, ensuring only the required amount of heating and cooling water is distributed around the centre means that pump energy can be reduced to supply only the required flow to the centre. With such enormous floor plate, reliable sensing data to the BEMS is key to realising significant energy savings, as well as ensuring year-round comfort conditions for the building occupants. In summary, accurate sensor information is an important part of building automation and should not be overlooked. Accurate sensor values can help save energy and provide high-quality information for data analysis systems. Using the correct sensing technology for your application can have a positive impact on occupant comfort and well-being. Considering smart sensors and wireless solutions at the outset of a project can offer long-term benefits and help reduce building lifecycle costs. If you have any questions, we are happy to answer any questions that have come up through this presentation. Please email inquiries@sonte-academy.com where we will get back to you with some answers. Thank you very much for attending this presentation.